Okay, now it is fine.
Okay, you all can see. Okay, so today I thank the organizer for giving me this opportunity to talk about this interesting topic of luminescent semiconductor nanocrystals. And this is I will be just talking about the basic fundamentals of why this semiconductor nanocrystals and why we are interested in it. So uh, so the outline here is that we will be talking about I will discuss this why first I will discuss what is semiconductor, why we are using semiconductor nanocrystals, uh, and why they are so interesting, and what is the reason, the basic properties, that quantum confinement and its effects. Then size dependent absorption will be discussed in some detail, because that is very crucial in determining the quality of nanocrystals. So I'll also discuss some theoretical models in which band gap and size has been correlated, and that can be used for uh, determining the size using UV visible spectroscopy. That is also well established now, even for size distribution also. So these are things that will be discussed in, and then the size dependent emission, that is the property, the light emitting property, that will be discussed. And again, I'll be talking about how this application you need for the uh, the quantum dots, the semiconductor nanocrystal has to be having very high quantum efficiency, photoluminescence quantum efficiency. So how we can achieve that? So those are the things that I will touch upon. It will be preliminary kind of things so that students can get the basics. And so here, these things, this description, nanocrystals, and it's this was earlier, if I say 20 years back, it was confined to the research labs only. But nowadays, if you look around yourself, you will find that they are impacting your lives, and they are now out in the uh, impacting lives of common man. So to mobile phone that you have in your hand, you know, we know already know that how, if you just what correlate what is the what was the status of that in 20 years back, that it used to be bulky, it used to be low battery life and less features. But now you have the things are, it is much, it has gone a metamorphosis, it has gone undergone a tremendous transformation, in which you all know that it is now performing more functions and having a higher battery life, even then. So this all things are packing up a lot more in a small space that has been possible because of nanotechnology. You have enhanced battery life because there are some nanotechnological components utilized in making this system. A recent example of this will be the Samsung. You must have seen the Samsung advertisement for QLED TV. So this, if you use screen, this is the display screen technology that has been developed by Samsung, and the Q here stands for quantum dots. And these quantum dots are a special type of semiconductor nanocrystals, which I will discuss uh, in coming slides. So this QLED is transforming the way display system work. It is also transforming the lighting. The new lighting technology is coming up, which will cost only a fraction of your electricity cost and give more output. So these are things that everyone can feel. We have to know, the students should know about it, how it works, and what are the responsible thing, material that is used in your mobile phones, in your computer, TV, computer screens, and so on. So not only that, those the semiconductor nanocrystals, we are looking for this source of energy which are renewable, which because we all know that the fossil fuels are depleting. and we are having, in a few years from now, we will having energy crisis. So if we have to switch to this renewable sources of energy, which so that the development can be sustained. So and solar power is solar cells have come up as a good alternative. Even in this case also, semiconductor nanocrystals are playing a big role. As you can see here, just a schematic is given over here. The details would be covered in some of these details would be covered in the next talk. By the application part will be covered in that talk next to me. By Shovan Patra from Tata Steel will discuss those aspects. And so I will just touch upon those points. What are the key properties that is makes them so interesting, and they got so many application in so many things, even in cosmetics. Look here, it's like even zinc oxide is a semiconductor. It is nano zinc oxide is being used in this even in cosmetics for protection from UV light. So these are very interesting things that we know. And there's also upcoming things like in diagnostics and therapy. So semiconductor nanocrystals are going to be very important. They are already important, and they are going to be even more important in the times to come. So so first thing, if you look at these nanomaterials, there is something unusual, and they show some properties which are unusual and superior. There's some properties which you could not have thought of, say 25 years spectroscopic state of the system. Like, for example, if I give you the example of silver here, which is a metal, if you convert into nanoscale materials like this, you'll get a variety of colors. So this is something possible because of when the size is reduced to in general, we say that 100 to 1 to 100 nanometers. So 100 nanometer and lower sizes will show this kind of typical properties. These properties were not imagined, could not be imagined, say 25 years back, because there was there's not enhanced research activity in this field. So this is a field that has taken up, caught the imagination of scientists around the world nowadays. And because of, so these nanomaterials are something that we define them as unusual. They show unusual and superior properties compared to the bulk substances, that is a big crystal of silver. And if you are comparing with the molecular state, a single atomic molecular state of silver, it is different from all of that. So we also say that they are intermediate state of matter, which were not explored before. Here is an example of cadmium telluride. It looks black in color when it is a very big crystal. When you reduce it to a very small size, such as less than 15 nanometers, 5 nanometers and below, you get a variety of colors. This picture that you are seeing is taken in my lab in a UV light. So this, you can see the sizes are mentioned over here. So this is a semiconductor. So this semiconductor is very, very sensitive as compared to the size. You can see here 3.2, even 0.2 nanometer change in size can give so much variation in colors. These are emission colors, that is fluorescent colors that we are seeing here. So they are very sensitive to, I think amongst all solid materials known, this is a class of material which is the most sensitive in terms to optical properties with respect to change in size, as you can see here. So I'm touching, going from the very basics. So what you can see here, that the inorganic solids, generally they are they have a band structure. That is, so you have this, so you have insulators which have very high conduction gap between conduction band and the valence band. Then you have semiconductors which have smaller gap, and this gap, if you so that they can be, if you increase the temperature you can get the conduction. It starts conducting. So that's the why we call them semiconductors. And then you have the metals, which I just showed you about silver and silver nanocrystals. So they have overlap of conduction and valence band. So today our focus is on this semiconductor system. This is the nature of the bands. In case of when it is a bulk crystal, that is we are talking macroscopic, a very large, big crystal, micron size and above, they will be having this kind of structure. But when you decrease the size, make it smaller, let's see what happens. There's a basic phenomena that is called most of the properties that we see in semiconductors, nanocrystal, can be understood in the domain of, that is in quantum mechanics terminologies. And just like it is related to the what we have, it is to the motion of the charge carriers inside the crystal. So for this is a class. This slide gives you a classic example of that particle in a box model, electron in a box. Here we have said the charge carrier, and so if we know that in such cases, this is the ABC, the side of the cuboid, and then we can have if the potential out inside the inside is 0 and potential energy outside is very high at the walls. So in such cases, we have waves. The particle which is there, it will have de Broglie waves, which will have such profiles. And this can be obtained if we solve this Schrodinger equation, apply boundary conditions. The solution comes like this, and this solution, this is gives you for A, B, C. If all this is these are different, then it will have this kind of solution. And in case of in a simplified approach, if A, B, C are equal, then the separation between energy levels will be square of the cube dimension, inversely proportional to the square of cube dimension. So this inverse proportionality is there. So as you decrease the size of this box, the spacing between the two energy levels will increase. So let's see how this thing, quantum mechanics particle in a box model, have been taught from early times in the quantum mechanics. But now with the advent of these semiconductors, nanocrystals, it is now possible to make such structures which resemble particle in a box in a real system. In a real structures, we can achieve this kind of things. We can see this increase in energy levels, energy spacings with respect to decrease in the dimension. This is so this is something that we are going to I'm going to discuss on next slide. So there is something in the semiconductor, the charge. We need to understand that the charge carrier is a exciton. You have electrons in the valence band. Conduction band is empty. When you give when light is made incident upon the semiconductor, electron is excited, and electron hole, it leaves back a vacancy which is known as hole. So this electron hole pair is known as exciton. So this is energy level diagram, and there is something called Bohr exciton radius, which shows the separation of this hole and electrons. And this separation not in this energy diagram, we have to look at in the Cartesian coordinates in a real crystal system, electron hole. So that separation is called Bohr exciton radius. It is easier to understand it. The exciton could be easily understood by taking the model developed by Niels Bohr to understand hydrogen atom. So in case of hydrogen atom, as we all know, Bohr's model, proton is at the center and electron is moving in a circular path like this. So instead of, you just have to do one thing, replace this proton with hole. The positive charge P plus that was proton is replaced by hole, and this becomes your exciton. So this is a system that is generated upon excitation. When the light is absorbed by the semiconductor, this electron hole pair is generated, and this is the charge carrier which moves throughout the crystal. When you see this, so this average separation between the holes and electrons in this manner is called the Bohr exciton radius. We also call it, so if this is the radius, this part will be called diameter. So Bohr exciton diameter is more relevant term to us in nanotechnology, because the sizes, if we say particle size, crystallite size, we usually refer to the diameter of the crystal. So it is easier to compare diameter of exciton with diameter of crystal, and then we can discuss more that will be easy to discuss. So this is a typical example, because cadmium telluride is a system that we have worked for quite. We as well as some other research groups have also worked upon, and the properties have been quite well understood. So this is a thing that so Bohr exciton diameter will be different for different systems. Mass of electron and holes pairs, reduced mass, we have to take the reduced mass of electron hole, and so it will be different for different system. Typically for cadmium telluride, it has been calculated to be 7.5 nanometer, and diameter of the semiconductor crystal, if it becomes smaller than the Bohr exciton diameter, then we are going to see a very different kind of properties, a blue shift in the spectrum. There is enhanced fluorescence, quantum yield. So these are the things that becomes very interesting, which is not seen in the molecular cadmium telluride molecules or cadmium telluride bulk crystal. It is only seen in these nanocrystals, which are smaller than a particular threshold values, particular size, as told here. So the diameter has to be smaller than the Bohr exciton diameter. The crystal diameter has to be smaller. So this is the essential criteria below which we will see this kind of thing. To understand this even better, I'm taking this. Sorry. Okay. So to understand it better, we just take it. So in case of if you have a very big crystal, a very big crystal, and the exciton is your particle, so it will see you. It will find it can travel. It has no bound restriction. It can execute free motion in x, y, and z directions. Okay, so that is the case. Exciton can execute free motion in a bulk crystal, in a big microscopic system. So now we slowly decrease the size of this box, the box in which the exciton is kept. So then you will find there will be some it is still free to execute. It can, because the dimension is very large, still it can execute free motion. But after some time, when you are making it smaller and smaller, the restriction is more, and finally you will reach a point when the size of the crystal, size of the box that we are talking about, is almost comparable, is almost equal, almost it is on the order of the Bohr exciton diameter. In such cases, this exciton will not be able to execute free motion. So if we are able to execute this thing in all the three, not able to move easily in any of the three dimensions, that is a quantum dot. And so this is, we say that the exciton is now confined. You can further decrease the crystal size below the Bohr exciton diameter, the confinement gets even stronger and stronger. So as you decrease this, so what happens, this is the quantum confinement, confining, restricting, putting a restriction on the motion of the charge carriers, the charge carrier here being exciton. So so when once you reach this stage, size, one slide previously and this one, so then this quantization of energy, this separation of energy levels changes, and you will see new properties as discussed earlier, and many more things will be discussed. So you will be seeing depend as you decrease the size, the band gap increases, the absorption colors, something which was looking black earlier, just like cadmium telluride, which was looking black because it absorbed in the NIR region around 800 nanometers, starts absorbing in the at 600, 500, 400 as you decrease the size below 15 nanometers and so and less. So this kind of thing is the quantum confinement. So the confinement of the exciton, putting a restriction on the motion, free motion of the exciton. If you are achieving this in all the 3 dimensions, so there is so this is so to sum up the things, the phenomenon that we are talking about relates to spatial confinement of charge carriers in 3-dimensional space. That is, we are talking about restricting the motion of exciton in 3-dimensional space so that it is not able to execute free motion, and then the quantum mechanical properties sets in. At that point, that is the point, once you achieve that, the quantum mechanical properties sets in, and you see a number of effects which will come up, which, so this, once this essential condition is met, you have uh, you will have a number of effects which will be shown up as the discretization of energy levels will be there. What does this mean? Discretization of energy levels means that initially we are looking from a big crystal. First, we are starting from a bulk crystal, and then we are moving towards slowly, gradually, we are moving to smaller and smaller sizes. So what happens when we are moving to smaller and smaller sizes? The band structure is getting severely affected. The bands, that is a continuum of energy levels, in no more, it is slightly that gets discretized, and the discretization is more and more as you go to the, so the discrete energy levels start appearing in between the bands, and that will, I'll just so not in the band structure, and that I'll show. So there will be increase in the energy gap between the, if you are calculating the from the conduction band edge, that is the bottom of conduction band and top of valence band. So that gap, that energy gap will go on increasing as you decrease the size, and so here onwards you will see a change in size. You will see size dependent optical properties. So so this quantum confinements in 3-dimensional space in, so it can be achieved. So this picture it gives you, this is a bulk crystal in which the size, the dimension, the XYZ direction, the axis, if you take 3 axes, along 3 axes, the length is so large that the exciton sees an infinite distance that it can travel. It is free to move. So that is a bulk crystal, and you have the density of state profile is like this. When you reduce one dimension to the nanoscale, and not in nanoscale, in nanoscale also you have classification, like you have to, if you reduce it below the board exciton diameter, say only one direction, say X direction is reduced to that level, you will see, so in this dimension, the exciton is confined, it is no longer free to move, but in other 2 dimensions, it is ready to move around. So this kind of thing will be called a quantum well, and it will have this kind of step-like density of state profile. Similarly, now we go to another level, that x-axis. Now we also reduce the size in the y-axis direction, along the y-axis, so that it also becomes smaller than the Bohr exciton diameter of the concerned semiconductor. In that case, in 2 dimensions, the electrons, the excitons will not be able to execute free motion, and only in one direction they will be executing free motion. So, and there is a final thing that we have shown here, is that in all 3rd dimension which was left over, in that also you reduce the that the length scale is reduced in that direction, and that below the exciton diameter. So now in all the three dimensions, the exciton is not free to move. It cannot execute free motion in any of them. So in that case, it has no dimension available to execute free motion, and we call it zero dimensional system. So dimensionality of a system is defined based on the uh, the dimension that is available for the charge carrier to execute free motion. The dimension that is available. So if you, so that is, so just now as I told you that it is a quantum dot is said to be a zero dimensional system, or we say that it is confined in all the three. We have achieved three-dimensional confinement. Both a correct way of expressing the same thing. In quantum wire, you have two-dimensional confinement, and it is said to be a one-dimensional system because the exciton can execute free motion only in one direction. So in a nutshell, this can be summarized in this way: exciton confined in one direction, we call it thin film. This is the cases of thin films. We call it quantum well. Excitons can easily move in two dimensions, and then you have exciton confined in, there are two dimensions which in which exciton is confined only in one direction. It can move easily. And the third last case is that of this thing is that in all the three dimensions, the size has been length has been reduced, and below the Bohr exciton diameter, in such cases, exciton can easily move in zero. That zero dimension is, so that's why we call it low dimensional system, and particularly the quantum dot will be called. So this dot, the word dot symbolizes the lost dimensions. Just like you put a dot with a pencil on your paper, you won't be able to measure length, breadth, or height, anything. So it has no dimension. We say that a dot doesn't have any dimension. Similarly, this quantum dot, the term dot symbolizes that loss of dimensions with respect to the free motion of the excitons, as I discussed. So this is a table showing a compilation of which shows the Bohr exciton diameter and band gap energy of different semiconductor systems. Particularly interesting are this cadmium selenide. The most worked upon semiconductor is cadmium selenide. There's initial work entirely focused on cadmium selenide semiconductors, cadmium telluride, cadmium sulfide. These three represent the bulk of the research work in semiconductor nanocrystal has been done on these systems. Uh, uh, because why they are interesting? Because they are direct band gap semiconductors, and when they are reduced to this low dimensional systems, reduced into a low dimensional system, as I just discussed, when you make small nanocrystals of these, they can emit light of different colors. Entire visible spectrum can be regenerated using their emission colors, the fluorescent colors. So it is helpful in terms of making LEDs, and also making some other things like bioimaging, developing some bioimaging techniques. Uh, However, that has been debatable because of some toxicity issues also came up later on. So that while, but so far as LEDs and other things are concerned, they are fantastic. And even in as I showed in one of the introductory slide, that was in case of cadmium sulfide, and these are used for solar cells. So we have all the systems enlisted over here. So you can see here the cadmium telluride is a system which is having 15 nanometer is the Bohr exciton diameter, and so practically what it means that I have to make a nanocrystal which is smaller than 15 nanometer to observe this quantum confinement effects, to see the change in colors, as I shown in previous slides, in introductory slide, that a black color initially cadmium telluride looks black, it absorbs in the around 800 nanometers, and so it is completely like it is not fluorescent. The bulk cadmium sulfide is not fluorescent, but when you reduce them to such a small size, for cadmium sulfide, if you have to reduce it below 5 nanometers, then you see that they become fluorescent. They emit light. on excitation with photons. They also show electroluminescence property. Electroluminescence is also important because that is the thing we use for this thing making LEDs, because electric current is passed and that excites the electron, and the rest of the relaxation process gives us the light. So if you look carefully, this is how this is a picture that shows a series of quantum dots uh, with of different sizes. The crystal size, the spherical sized nanocrystal, which has which has diameter lower than the Bohr exciton diameter, are called quantum dots. So in this case, so you can see blue emission to red emission. The material is same. It is cadmium selenide, and so this is red emitting light. Red light emitting quantum dot is larger in size, and gradually, if you are moving from right to left, the size is decreasing, and the smallest size nanocrystal emits blue light. So what is happening if you're looking from the point of view of bulk semiconductor? This is what I told you, that there's two bands, conduction bands and valence band. But when you decrease the size below this threshold value of Bohr exciton diameter, there is the discretization begins. Discretization begins. This is what I show here. What is shown here over here. There is increase in the gap. There is increase in the gap. There is also increase in the the some of this. Now you can see here. Here is complete continuum, but after that there is some gap has come, and then there's small continuum gap, and then even smaller continuum, and finally at the top you are looking at a discrete energy level. So this is what we mean by this beginning of the discretization of energy levels. So the continuum is slightly getting less. So you have partial band-like structure and partial molecule-like discrete structures. So and as you go from a nanocrystal to small nanocrystal, this the discretization is more and more prominent. And the ultimate thing will be you will be reaching a thing where you have one cadmium, one selenium, and that will form a cadmium selenide molecule. So in that case, you will have completely discrete energy levels. That is a molecule in case of molecule. So that's what uh, I said earlier, that it is there. They show properties which are intermediate between those of bulk crystal or molecular crystal. It is so prior to, so that's why it makes interesting, because you something which was not fluorescent earlier turns into a fluorescent material. It's in case of quantum dots, the electron hole recombination is enhanced, radiative recombination is enhanced, and so it also it is shown reported in literature that 70 to 85% up to is quantum efficiency, luminescence quantum efficiency has been achieved. So these are the effects of quantum confinements, and what we see here is the absorption spectrum of cadmium sulfide. So there are two important things that you can see here. Cadmium sulfide bulk, there is absorption, uh, but there is no well-defined peak. As you decrease the size, I showed in previous slide, the Bohr exciton diameter was 5.6. So here we are approaching, just approaching that CDS 6 nanometer shows the size where we are approaching that Bohr exciton diameter. And so from here onwards, you are seeing a shift. And this profile, you can see gradually this absorption peak is enhanced. We have uh, gradually enhancement of this excitonic peak. There is a blue shift. So we say that the energy, sorry, sorry, is this, so this
Please
is
mute
something.
your mic.
Okay, so this is something which is So there is blue shift. That blue shift means decrease in energy of the absorption peak. So that is what we are seeing. We can also see they are well defined as you move to the lower sizes, smaller sizes. In case of quantum dots, 6 nanometers and below, 2.2. The in addition to the blue shift, there is also enhanced peak here. So this enhanced it is becoming sharper and sharper in spectroscopic terms. So in spectroscopic term, we talk about half width at a half maxima, HWHM in this case. So that you can see it is becoming very, very less. And so this is because in case of bulk case, the exciton binding energy is uh, very less. It is on the order of if it is a few MeVs, a few tens of MeVs, which is equal to the thermal energy. So the exciton is not really tightly bound together. So it's because exciton binding energy is equal to thermal energy, so when it is easily thermalized, and you don't see a typical exciton peak. But when you as you decrease the size, there is enhanced overlap of electron and hole wave functions. The de Broglie wavelength of electron, the de Broglie wavelength that you calculate for holes, they are especially in a very closed space. They have been packed, so they have a very high overlap amongst themselves. So spatial overlap between electron and holes makes this exciton bind. Because of this, the exciton binding energy increases, and that is not so that is not able. So they are tightly bound, and you need some energy to unbound that electron hole pair. So that is we see a clear profile by a clear peak, because that can only be done by a photon. When a photon is absorbed, then only that energy can be overcome, not by thermal. It cannot be overcome. The binding energy cannot be overcome by this thermal energy. It has become much higher, and we are getting an enhanced peak like feature. Distinct peak is observed in the absorption spectra for quantum dots. So two things are there in the absorption thing, and this absorption profile is so. In the first section, I am only discussing this absorption profile, and then I'll also move to the photoluminescence part. So the absorption part that I've just shown over here, it can be used to calculate the band gap very easily. So, and the band gap can be correlated with the bulk band gap, and which is shown over here. This is the ER represents R. Capital R is the radius of the crystal, radius of the semiconductor nanocrystal, and E is the band gap, energy gap in the semiconductor nanocrystal. EG represent the bulk band gap in the bulk crystal, and this term is the kinetic energy term, which gives you the which is relates it to the effective mass of the system, for effective mass of hole, effective mass of electrons. The next term is the Coulombic interactions. So you can see just like typical electrostatic interaction kind of thing. So that is shown here. And the last term is the special correlation between the electron and holes wave function. So this was an explanation in the early is when this work was started in around 82, 84 by the first quantum dot was made by Ekimov and Efros, and after that Elie Bruce reported the synthesis. So they had derived this kind of equation based on the effective mass calculations, and this was able to explain the change in the band gap with decrease in size. But there were some problems with this. When you go to the very low sizes, although it provided good description of blue shift, that why it shifts, and that from the when a threshold value of size is reached, that was explained, but it was not matching exactly matching with the experimental result. Particularly, the numerical values that was determined for the band gaps and sizes, that was not exactly matching with the experimentally determined value. Particularly for sizes less than 7 nanometers, the description was woefully short, and it was not sufficient enough to describe their structures. So there was need for new theories to be come up, theories to be evolved. And it also, there was another big problem with this, was that band gap values get overestimated in comparison to the true value of this small crystal diameter. And so right now, so in between there was a pseudo potential theory which came up, but right now this tight binding approximation is the main theory that clearly that evolves, that gives a very good description of the sizes and optical absorption. And this band gap and size is very correlated, well explained by tight binding approximation. uh, Students may correlate with this. Tight binding approximation can be understood in terms of uh, combination of atomic orbitals of all the crystals taken together, just like you are making a linear combination of atomic orbitals for molecules. Extend that to the entire crystal with some changes, and then you make an entire crystal orbital. That is what is done in tight binding approximation. And when you do that, the results were very well matching with the experimental results. And this is what is shown in my slide over here. So these are the works by Professor Dipankar Das Sharma from IISc Bangalore, which was reported in Physical Review B. So you can see here they had there's so these on the y-axis you are seeing the band edge shift. We have the conduction band edge, we have valence band edge, and edge to edge difference gives you the band gap. So, and on the x-axis, what you are seeing in terms of Armstrongs is the diameter of the nanocrystals. So as for example, the ZNS1 is shown over here for 80 angstrom, 60 angstrom. So as the size decreases, you can see the conduction band edge. That is what you normally say the conduction band edge means bottom of the conduction band that goes up like this, and the top of the valence band, that you can say the valence band edge, moves down. So if you calculate the difference, the gap, energy gap, will go on increasing. So similarly with other cases, cadmium sulfide, you will have similar profile. Of course, the values on x and y axis will be different because as I said, the boric atom diameter will be different in different cases. So the threshold, and you can also see that when you are approaching sizes for cadmium sulfide, you can see by the time you are approaching 80 angstrom, that is 8 nanometer, you won't see it becomes flat. It becomes asymptotic, and you will have a fixed band gap. So somebody working on the semiconductor nanocrystals will see the unusual and extraordinary properties only when this threshold barrier is crossed and you are coming below this size regime. So which is the cutoff size is determined by the Bohr exciton diameter. So you have to make sizes smaller than that to absorb this extraordinary properties of fluorescence and absorption that we are discussing today. So cadmium sulfide is also so in this
Sir,
manner.
let me interrupt, sir. Another 5 minutes, sir.
Only 5 minutes. Okay. So this I'll try to finish. So this is zinc sulfide. So these are what we are seeing here: band shift in the bandage, shift in the band gap. So this is the kind of profile, and the one in the central, the dark line that you are seeing, is the tight binding approach. The other two lines are effective mass and pseudo potential theories. So best and the cross these points that you are seeing are experimental results. So a good matching of the theory and experimental results is you can get it from in the tide binding approximation. So this is the accepted approach now for all the semiconductor nanocrystals. And I'm also telling you a method how we determine the band gap. So this is the absorption spectrum we acquire as acquired. So you can see this is a typical absorption spectrum of cadmium telluride nanocrystal. And this is for cadmium sulfide nanocrystal. And then you can convert it into, you can change the axis, you can convert it to photon energy, and then take this differentiated dA by dE, and the peak over here, that gives you the band gap. So this is a slightly better way of determining it is a better way of determining the band gap as compared to tau equation, which is conventionally used. And you can see here only 1 point we are getting. So even if there is when you differentiate and things, it is so okay. So this is how we determine the band gap from this position, top position, and then we correlate with the, we have the, if we have this we have also have equation of tide binding approach which matches with the theory. So if I don't know the size, I can determine the band gap by using this UV absorption technique, and then after determining the band gap, fit it into this equation and find out the size. And this approach is really helpful when you are studying a large number of semiconductor nanocrystal. You are trying to follow a growth profile of the system. You cannot go on and do TEM for all of them. So you can take few samples and get it. You can see that they are matching with the experiment TEM results also. So what you are determining with this is accepted, and in this way it can be done. There is also a way that was again suggested by Professor D.D. Sharma and group, that we can also determine size distribution based on this, because in a given sample you have an ensemble of particles, and which will be of slightly different sizes. So if they have slightly different sizes, there will be distribution of size, particle sizes. There will be also a distribution of band gaps. So by estimating this FWHM and the energy value over here, it is possible to calculate the, by taking the difference divided by the mean, we can calculate the distribution, size distribution, and which can further be correlated with the actual distribution determined by TEM. So this is possible. These are the things that is interesting and it can be done using. So only from UV visible spectroscopy, there are many more information that we can extract. UV visible absorption spectroscopy, you can also determine the size as shown over here. This is another work by Peng and group from USA. So spectroscopy leads to absorption spectroscopy is giving you three things: size distribution, band gap size distribution, and the concentration. So these are the things that is possible to. These are some of the works that we did on cadmium telluride. So you can see we can by changing the size, it was possible to get the fluorescence in the entire visible range, and the peaks absorption. The key feature is that the fluorescence peak is narrow, very sharp. The absorption peak is there, but there is a continuous absorption here onwards. So there is a we can say that it absorbs in a broad range beyond the threshold value, but the absorption profile will always be sharp. So broad excitation and narrow emission is the key feature of this nanocrystals, which can be utilized for device applications. We also followed growth kinetics and nucleation and growth kinetics using this as the nanocrystal is growing in the vessel, round bottom flask. We can take aliquots at different time intervals and follow the growth of, so growth kinetics was followed. We also determine how the size distribution changes as the growth continues. And so luminescence for students, it is important to understand that these semiconductor crystals that we are talking about are basically direct bandgap semiconductors which have enhanced light matter interactions. So a direct bandgap semiconductor, you know that it has the K values at the top of valence band and bottom of conduction band at the same K value. And so there's the conservation of momentum is followed, and the transition is allowed, and they absorb light prominently, not frequently. So absorption and fluorescence both are facilitated. But in case of indirect band gap, that is not the case, and conservation laws of momentum is not followed, and you can't make a light emitting device using this kind of thing. It will be difficult. So this kind of system is preferred. So when you have to identify a semiconductor system, we go by this. And then so luminescence basically is emission of electromagnetic radiation as a result of electronic excitation. How you carry out that electronic excitation, how you create that excited state, based on that you have classifications such as photoluminescence, that is excitation by photon, or electroluminescence, when you drive a current through a circuit and the electrons are excited, and when they relax back to the ground state, they emit light. So these are electroluminescence, photoluminescence, both are very well studied for these systems. So these are typical textbook things, Javelinsky diagram. And so important thing is over here that normally if you have a semiconductor system, semiconductor nanocrystal, there are a lot of particles, the surface to core, surface atoms to core atoms, the ratio of that goes on increasing as you reduce the size. And the surface atoms have unsatisfied valencies, unsatisfied coordinations, and these give rise to these trap states. There will be deep and shallow trap states, and so if they capture the electrons and holes, then the radiative recombination of electron hole won't occur, and you will have problem. You won't have a. So you need to get rid of these unsatisfied coordinations. We also call them dangling bonds on the surface, the unsatisfied valency and those things. So we have to get rid of them to get an enhanced fluorescence yield, quantum yield. And to do that, I'll just talk about that. We use this surface capping technique. We attach certain amphiphilic ligands on the surface. These are amphiphilic, means one end of it is a long organic molecule, long chain, one end of which has affinity for the cationic sites on the surface of a nanocrystal, and the other side has affinity for the what we call solvent, because generally we synthesize in colloidal system. So this is very essential that so once they are coordinated to these ligands, capping ligands, we also call them capping ligands, then they are able to, that dangling bonds are gone, and your fluorescence quantum yield will be higher. Moreover, they will also impart enhanced stability to the system. So this is the thing. And so we usually work with the aqueous system, and we have used thiols as in our papers, that's shown over here. So and they also have the thiol end has an affinity for the particle surface, and the other end is free, which can be used for coordinating with the water. So these are the system and photoluminescence. So there's another approach by which we give a coat of higher band gap material on the top, a few layers. So inside is CdSe, cadmium and selenide atoms, and on the top zinc sulfide is there. So once you do that, you also satisfy the unsatisfied coordinations, and in this way the trap states are removed. So that is a typical work. So this is a valence band, conduction band. These are the trap states, and once you overcoat them with a higher band gap material, that these trap states are removed completely. So this is a very good way of doing this. So such core shell structures, higher band gap material on the top and smaller band gap as a core, gives a very high quantum yield. And the way to calculate is like this. I'm not going into details of this because of shortage of time. We evolved a new way of improving this quantum yield without coating, overcoating of a higher bandgap material, and that was the way that we discovered that is called supersaturation controlled approach, in which remember there are three features, essential features of a growth process. When you formation of a nanocrystal from solution phase, there is supersaturation, nucleation, and the crystal growth.
Sir, we are going late, sir.
Okay. So this is my last, and yeah, so this is the last, and I conclude here. So semiconductor nanocrystals have show this enhanced feature, unusual properties because of quantum confinement. Correlation of band gap is better observed, explained by tight banding approximation, and band edge luminescence and enhanced PLQE can be observed by overcoating with a ligand, ambiphilic ligand, or you can have another layer of semiconductor. And because of these features, these nanocrystals are very suitable, very much suitable, very much they can be utilized for device applications such as light emitting devices, QLED, just as has been discovered by Samsung, invented by Samsung. And so there are other applications which are coming up, and so this is a very exciting field. These are my group members. Shobhan Patra is now Tata Steel. He will be giving next talk, and the others, Bhavesh, and is working. He was in KIT, and prior to that, he worked with me as research fellow. So these are Dr. Bhavya Bhushan. This was my first PhD student, Dr. Shatrupa Patnaik. So these are the acknowledgements for funding agencies. So thank you. So I thank you all for being patient with us.
So very informative and nice presentation. Now it is open for questions.
Thank you, sir. Yes.
One of the question from Lipsa Mishra, sir, you can see the chat box. How to determine in which system we can get direct band gap, in which system can we get indirect band gap? Just sir, please the chat box. See, Lipsa Mishra.
Sorry, just a moment. I'm not chat box. Okay. There are many things. What is the slide size?
Susan, sir, please repeat the question. Sir, repeat the question, please.
Okay, from Lipsa Mishra, how to determine in which system we can get direct band gap, and in which system we can get indirect band gap.
Indirect band gap.
In which system? Our question is in which system?
There are already results are there for most of the semiconductor system. You will find that it is already recorded, and by understanding that it is, as I showed, it is a band structure that determines, tells you about whether it will be direct band gap or not. So you have to work out, and you will also find practically you will find that light matter interaction is if it is for substance is good, then it is likely to be at a first preliminary thing, it will likely to be a direct band gap system if it is an unknown system. So we start from there, and then we work out the details, and it can be done.
Another question, sir, from Onimes. You can see the chat box. How one can prepare? Let me see the chat box.
How to select the suitable capping agents?
How one can ensure the direct or indirect band gap of the synthesized inorganic nanomaterial?
How
one can ensure the direct or indirect band gap of the synthesized inorganic nanomaterial?
No, that has to be determined prior to synthesizing your nanocrystal. Why?
Whether it is direct or indirect.
In the bulk, you work with in the bulk system, you determine whether it is direct or indirect. Once you start synthesizing, going into nanoscale, and then why we do do so much for something. You just determine first, ensure you be sure about it that it is a direct band gap, and then you can work out on the fluorescence part if you are interested.
Yes, sir.
Yeah, it is basically absorption techniques, and you can use it for determining that. We can discuss it later. You can send other questions to my email, so I can also. There are a lot of questions I can bring up, but how to reduce the.
Another question from Shashank Patnaik. Sir, how physically we can distinguish optical and electronic band gap?
Optical and
electronic band gap. How will distinguish?
Electronic band gaps can be. There are 2-3 different ways of determining it. The electronic band gaps can also be determined by the electrochemical approach, by which you can also determine the band edge positions. So electrochemical band gap, conduction band edge by performing cyclic voltammetry technique, you can get the direct actual value of conduction band edge, actual value of valence band edge, and then you can determine the gap value. And similarly, you can so additionally in UV spectroscopy, you are getting only the gap value. But in case of if you apply electrochemical technique, that is, you can also get the actual energy level positions of the top of the valence band and the bottom of the conduction band, and that is very important for particularly for the catalysis. If we're planning a catalysis work, then actual edge position is important in that case.
Okay, sir. Last question from Govind Raj.
Yeah.
How to reduce the band gap of the metal oxides without adding conducting materials?
Without adding
conducting materials. Just you can see the chat box.
How to reduce the band gap of the metal oxide without adding conducting materials? We are not adding any material to a metal oxide. Like zinc oxide is already is a semiconductor, direct band gap semiconductor. You don't have to do. So we don't add any. No need to add any conducting material. We are not doing it anyway. We are simply starting from the in chemistry. We start with the bottom-up approach. We start with the ions, and slowly from individual ions, you will have molecular cluster, and then there will be formation of nanocrystals. So we